All right, let's try a little thought experiment. Imagine you're a huge math fan, and you have to pick just one single proof to show a friend to convince them that math is beautiful. What's the one you'd pick? Well, today, we're going to look at what might be the perfect answer, an absolutely gorgeous proof from 3D geometry that shows why slicing a cone gives you a perfect ellipse. So what does that even mean for a math proof to be beautiful? It's not just about, getting the right answer. A beautiful proof has to have style, elegance, a bit of a surprise. It's a solution that's so clever it almost feels like a magic trick, but so solid and logical you can't argue with it. And we're about to dive into one of the all-time greats. So the whole puzzle here really starts with the ellipse itself. It's a shape we've all seen, but here's the crazy thing about it. It has at least three, totally different definitions. And honestly, when you first see them, you'd swear they were describing completely different shapes. Okay, so definition number one. This is the one that's super easy to picture. You just grab a circle and stretch it. Imagine taking a circle in a graphics program and just pulling it sideways. That's it. Simple enough, right? Boom, you've got yourself an ellipse. All right, definition two. This is the classic art class method. You stick two thumbtacks in a board, we call those the foci, and you loop a piece of string around them. Then you pull the string tight with a pencil and just trace it out. The shape you get? An ellipse. And the really cool part is, no matter where you are on that curve, if you measure the distance from your pencil to each thumbtack and add them up, that number never changes. It's always constant. And that brings us to our third and maybe weirdest definition. You literally just take a cone, like an ice cream cone, and slice through it with a flat sheet of paper at an angle. The edge, that curve you create where the paper cuts the cone, yep, that's an ellipse too. It's why they're often called conic sections. Okay, let's just stop and think about this for a second. We've got stretching a circle, we've got the whole string and thumbtack thing, and we've got slicing a cone. I mean, those are three completely different physical actions. How in the world do they all end up making the exact same kind of shape? It feels impossible. Like it has to be a crazy coincidence, right? Let's really dig into that cone slicing idea for a minute, because it's the one that's the most counterintuitive. I remember when I first heard about this, I just couldn't wrap my head around how it could possibly create something so perfect and symmetrical. I mean, think about it. The cone gets wider as you go down, right? So shouldn't the part of the slice that's on the wider part of the cone be, wider? Like, shouldn't it bulge out and look more like a lopsided egg or something? But it doesn't. It's a perfectly symmetrical ellipse every time. So how do we prove that's actually true? And to make the puzzle even more interesting, there's this property called eccentricity, which is basically just a fancy word for how squished the ellipse is. A perfect circle, that has an eccentricity of 0. But then you have something like Halley's Comet, and its orbit is super squished. Now here's the thing. With the string method, you control that squishiness by how far apart your thumbtacks are. With the cone method, you control it by changing the angle of your slice. So the real question is, how on earth do we prove that changing the angle of a slice is the exact same thing as changing the distance between 2 points? It's wild. Okay, so this is where it gets really good. To connect the cone slice to our string and thumbtack definition, we need a flash of genius. Remember, the whole point of the string method is that the sum of the distances to those two foci is always the same. So that's what we have to prove for the cone slice. And the way we're going to do it? It's not about crunching numbers, it's about building something beautiful. And here's the big reveal. The stroke of genius is to add 2 spheres inside the cone. Just picture it. One sphere sits neatly above our slice, and another one sits right below it. They're placed perfectly so that they're just touching the cone all the way around in a circle, and they're also just touching our slicing plane at a single point. These are called Dandelin spheres, an incredible idea from back in 1822. Now, this is what's so cool. These spheres are like the magic key that connects everything. Once you put them in the picture, the whole proof just unfolds. It's really elegant. Let's walk through exactly how it works. All right, let's break it down. First things first. Those 2 points where the spheres just kiss the slicing plane, those are our foci. They are the exact equivalent of the 2 thumbtacks from our other definition. Okay, next up. We just pick any old point on the edge of our ellipse. Doesn't matter which one. Now, from that point, we're going to draw a line to each of our new foci. And here's the last piece of the setup. From that same point on the ellipse, we're also going to draw a line straight along the side of the cone, one going up to the top circle where the sphere touches and one going down to the bottom circle. Got it? And this whole thing works because of one simple, really beautiful rule in geometry. It's called the tangent rule. Basically, if you pick a point anywhere outside a sphere and draw two lines from that point that just touch the sphere, that are tangent to it, those two lines will always, always be the exact same length. It's a perfect little piece of symmetry.
So let's use that rule right now. Think about our point on the ellipse. The line from that point to the top focus, it's tangent to the top sphere. And the line from that same point that goes up along the cone's surface, it's also tangent to the top sphere. So because of our tangent rule, what does that tell us? It tells us those two lines have to be the exact same length. And the same exact thing is true for the bottom sphere. The distance to the bottom focus is identical to the distance down the cone. So what does this all mean? Well, it means the sum of the distances to our two foci is exactly the same as the distance along the surface of the cone between those two circles of tangency. And since those circles are in a fixed position, that distance never changes. It's constant. It doesn't matter where you are on the ellipse.
And that's it. Bada boom, bada bang. We just did it. We've proven that any point on the curve from a sliced cone has that special constant sum property, which means it's the exact same shape you get from the string and thumbtack method. It's an ellipse. Proof complete. So let's bring it back to our original question. Why is this proof the one you'd show someone to convince them that math is beautiful? Because it's not just about the final answer. It's about how we got there. It's about the aha moment. This proof is it's a masterpiece. It takes two ideas that seem a million miles apart, slicing a cone and a loop of string, and shows they're secretly the same thing. And it doesn't do it by grinding through a bunch of nasty equations. It does it with one brilliant, creative move, putting those spheres in the picture. That single moment of inspiration, that's the heart of what real mathematical discovery feels like. You know, the mathematician Paul Lockhart said it best. It feels like magic. You look at it and you think, how could anyone have possibly thought of that? How on earth did they come up with the idea of adding spheres? And maybe that's the perfect final thought to leave you with. Because, yeah, it feels like a miracle. But what if that kind of genius isn't some inexplicable bolt from the blue? What if it's the result of just playing with shapes for years and years? So much so that an idea like, hey, what if I put a sphere in there, becomes a totally natural thought. And when you think of it that way, genius stops being this intimidating, magical thing, and it becomes something inspiring. It's not a miracle. It's the incredible, beautiful result of just being curious and putting in the time.